NASA Punch Mission, a historical and future perspective. Overview of the Punch mission. NASA's Polarimeter to unify the Corona and Heliosphere Punch mission is set to launch in late February 2025. This groundbreaking initiative aims to employ a constellation of 4 small satellites to conduct global three-dimensional observations of the Sun's corona. The primary objective is to understand how the mass and energy within the corona are transformed into solar wind, which has profound implications for space weather and its effects on Earth. The Punch mission is a collaborative effort led by the Southwest Research Institute SPHEREx based in San Antonio, Texas and Boulder, Colorado. NASA's Goddard Space Flight Center in Greenbelt, Maryland is responsible for managing the mission. Punch will be launched as a secondary payload alongside NASA's upcoming astrophysics observatory SPHEREx. Aboard a SpaceX Falcon 9 rocket from Vandenberg Space Force Base in California. Key milestones. Launch date, targeted for late February 2025. Launch vehicle, SpaceX Falcon 9 rocket. Launch site, Vandenberg Space Force Base, California. Mission components, for small satellites designed for 3D observations of the Sun's corona. Mission goals. The Punch mission has several critical objectives. 1. Understanding solar wind formation. The primary goal is to investigate the processes that convert solar corona mass and energy into solar wind, which affects space weather and can influence satellite operations and communications on Earth. 2. Global observations. The constellation of satellites will provide comprehensive 3D observations of the solar corona, enabling scientists to gather data that has been challenging to obtain with previous missions. 3. Enhancing space weather forecasting. By studying the dynamics of the corona and solar wind, Punch aims to improve our ability to predict space weather events, which can impact technology and infrastructure on Earth. Scientific collaboration and innovation. The Punch mission exemplifies the spirit of collaboration in modern science. It combines expertise from various institutions and disciplines. The lead institution, SPHEREx, has a long history of space science research, while NASA's Goddard Space Flight Center brings extensive experience in mission management and satellite technology. The choice to launch Punch as a secondary payload with SPHEREx also reflects a strategic approach to maximizing the scientific return on investment for space missions. By sharing launch resources, NASA can conduct multiple scientific investigations concurrently, fostering interdisciplinary research. Historical context. Understanding the Sun and its effects on the solar system has been a pursuit for centuries. Ancient civilizations worshipped the Sun, recognizing its vital role in their agricultural practices. Modern science has built upon this understanding, with missions such as the Solar and Heliospheric Observatory SOHO and the Parker Solar Probe providing valuable insights into solar dynamics. Punch is positioned to build on this legacy by offering a new perspective on solar phenomena. As the first mission dedicated to studying the corona in 3D, it promises to enhance our understanding of solar physics significantly. Future implications. The success of the Punch mission could have far-reaching implications for various fields. Space weather research. Improved models of solar wind generation will enhance our ability to predict space weather events, crucial for protecting satellites and electrical grids on Earth. Astrophysics. Insights gained from the Punch mission will contribute to our understanding of the Sun's lifecycle and its impact on the solar system's evolution. Interdisciplinary collaboration. The mission's collaborative nature may serve as a model for future scientific endeavors, encouraging partnerships between institutions and disciplines. Conclusion. NASA's Punch mission marks a significant milestone in our quest to understand the Sun and its influence on the Earth and beyond. Scheduled for launch in 2025, this innovative mission will provide groundbreaking insights into solar dynamics, advancing our knowledge of space weather and enhancing our ability to forecast solar events. The collaboration between various institutions underscores the importance of teamwork in tackling complex scientific challenges. As we stand on the brink of this new exploration, the Punch mission promises to illuminate the mysteries of the Sun, enriching our understanding of the cosmos and our place within it. NASA's Punch Polarimeter to Unify the Corona and Heliosphere mission represents a significant venture into solar research set for launch in late February 2025. The mission aims to enhance our understanding of the solar corona and the mechanisms by which solar wind is produced. Below, I will delve into some of the counterintuitive aspects surrounding this mission and its broader implications. Counterintuitive information. 1. Small satellites, big impact. While the Punch mission consists of 4 small satellites, the potential impact of their observations is substantial. Typically, one might expect that larger, more complex spacecraft would yield more significant scientific results. However, in this case, the small size and simplicity of the satellites enable them to be launched more affordably and flexibly. This approach allows for multiple satellites to be deployed as a constellation, providing a more comprehensive three-dimensional view of the solar corona than a single larger spacecraft could achieve. 2. Interdisciplinary collaboration. The Punch mission is a collaboration between various institutions, primarily the Southwest Research Institute and NASA's Goddard Spaceflight Center. While one might assume that collaboration among different organizations could complicate the mission due to differing goals or methodologies, it actually enhances the mission's capability. Each institution brings unique expertise and perspectives, leading to a more robust scientific investigation of solar phenomena. 3. Simultaneous launch with SPHEREx. Counterintuitively, the Punch mission is launching as a secondary payload alongside the SPHEREx mission, which focuses on astrophysics and the history of the universe. One might think that combining missions could dilute focus or resources. However, this dual launch maximizes efficiency and reduces costs, allowing NASA to conduct multiple scientific investigations simultaneously. The collaboration also underscores the interconnectedness of solar and cosmic studies, suggesting that understanding solar activity can provide insights into broader cosmic phenomena. 4. Focus on solar wind dynamics. Punch's focus on understanding how solar mass and energy convert into solar wind might seem like a niche scientific inquiry. However, understanding solar wind dynamics is vital for numerous practical applications, including space weather forecasting, which can significantly impact satellite operations, communication systems, and even power grids on Earth. This highlights a counterintuitive reality that fundamental scientific research can have significant implications for everyday technology and infrastructure. 5. Public engagement through historical context. The outreach efforts for the Punch mission incorporate themes from both ancient and modern sunwatching practices. One might assume that a mission focused on advanced scientific instrumentation would appeal primarily to a scientific audience. However, by connecting the mission to historical sun observation practices, Punch aims to engage a broader public interest, emphasizing the universal human fascination with the sun. This strategy underscores the idea that scientific exploration is not just a modern endeavor but part of humanity's long-standing quest for knowledge. 6. Significance of 3D observations. Traditional solar observations have often been two-dimensional, leading to challenges in fully understanding the complex dynamics of the solar corona. The Punch mission's 3D observational capability may seem like a technical upgrade. However, it fundamentally changes the way scientists can interpret solar phenomena. This shift to a multi-dimensional understanding can reveal previously hidden relationships and mechanisms within solar dynamics, a counterintuitive leap that emphasizes the importance of perspective in scientific inquiry. 7. Predictive potential for solar activity. The insights gained from Punch regarding solar wind and coronal activity may not only enhance our understanding of solar physics but also improve predictive models of solar storms. One might assume that such predictions are primarily based on historical data and current observations. However, the advanced observational techniques employed by Punch could allow for real-time monitoring and prediction of solar events, providing a proactive approach to understanding solar behavior rather than a reactive one. Conclusion. In summary, NASA's Punch mission encapsulates various counterintuitive elements that challenge conventional expectations regarding the relationship between satellite size and scientific output, the benefits of interdisciplinary collaboration, and the broader implications of solar research. By launching small satellites in a coordinated effort with a focus on 3D observations, Punch not only aims to advance our understanding of solar dynamics but also seeks to engage the public and enhance predictive models for space weather. These aspects highlight the innovative approaches employed in modern space science and the interconnected nature of cosmic phenomena. The NASA Punch Polarimeter to Unify the Corona and Heliosphere mission, launching in late February 2025, is poised to make significant contributions to our understanding of solar phenomena and their impacts on space weather. While most discussions around Punch focus on its goals and technical specifications, several critical aspects may be overlooked, yet are significant for the broader scientific context and future research. 1. Interdisciplinary collaboration. The Punch mission is a collaborative effort between the Southwest Research Institute and NASA's Goddard Space Flight Center, among other institutions. This partnership is significant as it exemplifies how interdisciplinary approaches enhance scientific inquiry. The integration of various expertise, from astrophysics to engineering, allows for the development of innovative technologies and methodologies that can be applied to other scientific fields. This collaborative model can serve as a blueprint for future projects, emphasizing the importance of working across disciplines to tackle complex problems. 2. 3D observations of the solar corona. While the mission's objective to provide 3D observations of the solar corona is frequently mentioned, the significance of this capability is often understated. Traditional observations of the Sun have primarily been 2D, limiting our understanding of the dynamic processes within the corona. By offering a three-dimensional perspective, Punch will help scientists better visualize and understand the structure and dynamics of solar phenomena such as coronal mass ejections (CMEs) and solar flares. These events can have profound effects on space weather, affecting satellite operations, communications, and even power grids on Earth. Understanding the 3D structure is crucial for developing predictive models of solar activity. 3. Connection to space weather prediction. The implications of Punch's findings extend beyond solar research into the realm of space weather forecasting. The mission aims to elucidate how the solar corona's mass and energy contribute to the solar wind. Solar wind variations can have direct consequences for Earth's magnetosphere and atmosphere, influencing geomagnetic storms and radiation exposure for astronauts. The insights gained from Punch could improve space weather prediction models, which is vital for safeguarding technological infrastructure and human health in space. 4. Partnership with SPHEREx. The Punch mission will be launched alongside the SPHEREx spectrophotometer for the History of the Universe Epoch of Reionization and ICE's Explorer mission. While Punch focuses on solar phenomena, SPHEREx is aimed at exploring cosmic history and the evolution of the universe. The dual launch presents a unique opportunity for synergies between solar science and astrophysics. By considering solar activity's influence on cosmic observations, researchers can gain a more holistic understanding of how solar phenomena may affect observational data from other celestial bodies and events. 5. Public outreach and education. The mission's outreach efforts incorporate themes of ancient and modern sun watching, highlighting the cultural significance of solar observation throughout history. This aspect is often overlooked in technical discussions but is crucial for fostering public interest in science and inspiring the next generation of scientists. By connecting contemporary research with historical practices, Punch can engage a broader audience, emphasizing the continuity of human curiosity about the Sun and its effects on our planet. 6. Technological innovations. Punch will utilize advanced technologies for its satellite constellation, which may include novel imaging and data processing techniques. The development and application of these technologies can lead to advancements not only in solar physics but also in other fields such as remote sensing, telecommunications, and data analytics. Recognizing the potential for cross-disciplinary technological advancements is essential for appreciating the broader impact of the Punch mission. 7. Impact on global scientific community. As Punch aims for global 3D observations of the Sun's corona, its findings will contribute to the international scientific community's understanding of solar dynamics. This global perspective is vital, as solar activity does not adhere to national borders and can affect different regions of the Earth variably. Enhanced international collaboration and data sharing can lead to more robust scientific conclusions and foster a sense of shared responsibility in addressing challenges posed by space weather. 8. Long-term data for future research. The data collected by Punch will provide a long-term dataset that can be invaluable for future research. Time series data on solar activity can help scientists identify trends and patterns that may not be apparent in short-term studies. This long-term perspective is crucial for understanding the solar cycle's effects on Earth and for developing predictive models that can anticipate solar activity's influence on human technology. Conclusion. The Punch mission represents a significant leap forward in solar physics and space weather research. While its primary objectives are well documented, the broader implications of interdisciplinary collaboration, 3D observational capabilities, public outreach, and technological innovations are equally important. By recognizing and emphasizing these often overlooked aspects, we can better appreciate the mission's potential to advance our understanding of the Sun and its profound influence on our planet and beyond. 1. Mission objectives and scientific importance. The Punch mission aims to provide a comprehensive understanding of the Sun's corona and the processes that lead to the formation of solar wind. By employing a constellation of 4 small satellites for 3D observations, Punch is set to unveil critical data about solar dynamics. This knowledge is essential for advancing our understanding of space weather, which can significantly impact satellite operations, communication systems, and even power grids on Earth. 2. Collaborative efforts in space science. The successful execution of the Punch mission highlights the collaborative nature of contemporary space science. Led by the Southwest Research Institute and managed by NASA's Goddard Space Flight Center, the mission exemplifies how different institutions can unite their expertise to tackle complex scientific questions. This collaboration is not limited to national entities. Similar partnerships often involve international agencies, enhancing the breadth of knowledge and resources available. 3. Technological integration and innovation. The Punch mission will be launched alongside NASA's SPHEREx observatory, showcasing the integration of multiple scientific missions into a single launch. This approach not only optimizes resources but also fosters technological innovation by allowing different scientific instruments to be developed and tested in parallel. The technological advancements gained from Punch could pave the way for future missions aimed at exploring other celestial phenomena. For future implications for space weather research, as our reliance on technology increases, understanding space weather becomes more critical. The insights gained from Punch will have far-reaching implications in predicting solar events and their effects on Earth. By contributing to the field of heliophysics, Punch will aid in the development of models that can forecast solar storms and their potential impact on Earth's atmosphere and technology, thus enhancing preparedness and risk management strategies in various sectors. 1. The Voyager program, 1977-present. The Voyager program, comprising Voyager 1 and Voyager 2, was launched by NASA in 1977 to explore the outer planets of the solar system. The mission aimed to gather data on Jupiter, Saturn, Uranus, and Neptune and their moons, providing unprecedented insights into the structure of the solar system. Voyager 1 became the first human-made object to enter interstellar space in 2012, while Voyager 2 followed in 2018. Both spacecraft carry the golden record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth, intended for any intelligent extraterrestrial life that might find them. The program has significantly advanced our understanding of planetary science and the heliosphere. Paralleling the goals of PUNCH in studying the solar phenomena and their effects on space weather. 2. SOHO Solar and Heliospheric Observatory 1995-present. SOHO is a joint project of NASA and the European Space Agency (ESA), launched in 1995 to study the Sun. It was designed to observe the Sun's internal structure, its atmosphere, and the solar wind, providing critical data about solar activities. SOHO has contributed to discovering thousands of solar and stellar phenomena, including solar flares and coronal mass ejections. Its continuous monitoring has allowed for advances in space weather forecasting similar to the objectives of the PUNCH mission, which seeks to understand solar wind origins and dynamics. 3. ACE Advanced Composition Explorer 1997-present. Launched in 1997, ACE was designed to study particles of solar, interstellar, interplanetary, and cosmic ray origins. The mission is critical for understanding the composition and dynamics of solar wind and its effects on the Earth's magnetosphere. ACE collects data on the elemental and isotopic composition of particles from various sources, providing insights into solar activity and its impact on space weather. This aligns with PUNCH's mission to investigate the Sun's corona and the transformation of solar energy into solar wind, contributing to our understanding of space weather phenomena. Future outlook: NASA's PUNCH mission. The upcoming launch of NASA's Polarimeter to unify the corona and heliosphere PUNCH in late February 2025 marks a significant step in solar research and our understanding of space weather phenomena. As we look ahead, several predictions can be made regarding the implications of this mission and its contributions to both science and society. 1. Enhanced understanding of solar dynamics. One of the primary goals of the PUNCH mission is to provide detailed 3D observations of the Sun's corona, which is essential for understanding the processes that lead to solar wind formation. This understanding could revolutionize our knowledge of solar dynamics. In the future, we might expect new models of solar activity. The data collected from PUNCH could lead to the development of more accurate models that predict solar activity, including solar flares and coronal mass ejections (CMEs). These models will enhance our ability to forecast space weather events that can affect satellite operations and communications on Earth. Insights into solar-Earth connections, as PUNCH investigates the relationship between the solar corona and heliosphere. Scientists will gain insights into how solar phenomena impact Earth's magnetosphere and atmosphere, contributing to our understanding of climate and weather patterns. 2. Advances in space weather prediction. With increased solar activity predicted for the upcoming solar cycle, the PUNCH mission's data will be crucial for improving space weather prediction capabilities. Future developments may include improved monitoring systems. The integration of PUNCH data with existing space weather monitoring systems will bolster real-time forecasting capabilities. This could lead to more effective warning systems for geomagnetic storms and other solar-induced disruptions. Public awareness and preparedness. As space weather becomes more predictable, public awareness initiatives can emerge to educate communities about the potential impacts of solar events on technology and infrastructure. 3. Contributions to astrophysics and cosmology. PUNCH is set to launch alongside the SPHEREx mission, which aims to map the universe's history. The synergy between these missions could yield significant advancements in astrophysics. Cosmic evolution insights. By correlating solar observations with cosmic background data from SPHEREx, researchers could understand better how solar phenomena influence the formation and evolution of galaxies and stars. Interdisciplinary research. The collaborative approach of these missions may encourage interdisciplinary research merging astrophysics, heliophysics, and planetary science, which could inspire new theoretical frameworks and experimental methodologies. 4. Technological innovations. The Punch mission will likely spur technological advancements in satellite design and data collection techniques. Miniaturization of instruments. The use of small satellites for extensive observational campaigns may lead to innovations in miniaturized instrumentation, making space missions more cost-effective and accessible. Data processing techniques. The volume of data generated by Punch will drive advancements in data processing and machine learning techniques, enhancing our ability to analyze complex datasets from space missions. 5. Educational and outreach opportunities. The excitement surrounding missions like Punch naturally leads to increased interest in STEM science, technology, engineering, and mathematics education. Engagement with the public. NASA's outreach programs related to Punch could inspire the next generation of scientists and engineers, fostering greater public engagement with space exploration. Curriculum development. Educational institutions may develop curricula that incorporate findings from Punch, ensuring that students are equipped with the latest knowledge in heliophysics and related fields. 6. International collaboration and policy implications. The Punch mission exemplifies global scientific collaboration, which may pave the way for future international partnerships in space exploration. Global scientific community. As countries increasingly realize the importance of understanding solar and space weather phenomena, we may see more collaborative missions aimed at studying the Sun and its effects on Earth. Policy development. Insights gained from Punch could inform international space policy, particularly concerning the management of space traffic and the protection of critical infrastructure from space weather impacts. Conclusion. The Punch mission represents a pivotal development in our quest to understand the Sun and its connection to the broader cosmos. As it embarks on its journey in 2025, the implications of its findings are likely to resonate across multiple fields of study, influencing everything from space weather prediction to astrophysical research and public engagement in science. The future outlook for Punch is not just about advancing our knowledge of solar dynamics. It is about fostering a comprehensive understanding of our universe and our place within it.